Okay, so thank you. So I'm going to talk about the results and the background research for this paper that we published on Archive last month, no, 2 months ago. So this was a project together mostly with Marina de Amicis and Gregorio Carullo and Simone Albanesi, who kind of worked on the perturbation theory aspect of this research, and I was taking care of the nonlinear numerical relativity evolutions that we have done here. So, yeah, okay.
Yeah, I will try to take care of this. Okay. So continue.
Okay, so this is sort of the main result. Okay, I think maybe people want to the mousepad doesn't work. So this can be this can be hidden. Sorry?
Okay, let me.
Here, plus. Okay, plus. Oh, it's all in French.
Yeah, of course. Now this thing, and then okay.
Okay. Now it looks good. So this is sort of the main result that we present also in this paper. So here you see the waveform, the post-merger waveform of a head-on simulation of 2 black holes. These are the mass ratios of the 2 black holes, and these are the lines that we have done for this SpEC, so in full numerical relativity, so fully nonlinear black hole evolutions. And then this line, this is a perturbative calculation. And there are a few remarkable things to say about this result. One is that this is sort of the first NR simulation where we actually show that we can resolve these tails very well. Yeah, in the past, because you see this is a logarithmic scale, this is like 5 magnitudes, 4 magnitudes smaller than the peak. So in the past, this used to be often within the noise floor of the simulation, so you couldn't really resolve it. But nowadays, the SpEC code is so accurate and precise that we can actually see these tails. Another important thing is that also the perturbative curve is actually in remarkably good agreement, although this is in the small mass ratio limit and only in linear calculation, sort of. The agreement is still remarkably well. There is, of course, some discrepancy, which we don't quite understand where it's coming from. But overall, this seems to tell us, for one, that the NR tail that we see here is actually reliable. Yeah, that it's not just by chance that we see a tail and actually it's something bad. And also that the perturbative model is relatively good. Yeah, so we don't quite know what is the exact reason for this growing relative difference. Yeah, maybe there's a nonlinear tail component. Yeah, maybe one has to go to second order perturbation theory to kind of close this gap, or maybe one has to include higher order effects in the mass ratio, not mass ratio. And of course, in NR, although everything decays towards a Kerr black hole, to a stationary Kerr black hole, there's still some time dependency in the NR simulation, which maybe has an effect that is not caught in the perturbative calculation. So that's just some ideas. We have really no idea yet what is a main cause of this disparity. So I give you now a brief overview about the perturbative treatment of these tails. So in 2023, there came out this paper by Simona Albanese and others, where they looked at such waveforms in solving a Raggeville-Cirilli equation, or the Raggeville-Cirilli equations. And what they found in this study is, so where you have a small point particle with a small mass, not infinitely small, but small, that approaches a black hole and then inspirals and merges or goes directly into it. They also do some eccentric simulations. And what they find is that this tail that I've just shown you is actually enhanced the higher the eccentricity of the simulation is. And from that, they then reasoned that probably the maximum tail magnitude you would get is that for head-on merger. And that's why also in this study, we looked at head-on mergers, because there we have the best chance to actually see this tail. So here, this is an example plot taken from this paper of Marina Dionikis. And you see for a quasi-circular inspiral, the tail is here. Yeah, it's really much smaller, in particular here at the end, it's like 5 magnitude smaller than that of a large eccentricity. Yeah, so it really makes a huge difference at what kind of simulation you look if you want to have a chance of seeing the tail. So whether you would be able to see a tail with SpEC in a quasi-circular in-spiral simulation, we don't know yet. That's probably too far into the noise floor to have reliable results, but if the eccentricity is high, there's a good chance. They also show this power law exponent that is decaying. So here it has some mild behavior, but eventually, asymptotically, it all goes to some value of -4. Yeah, so in the title of the paper and also of this talk, I actually used the word late time tails, but it's not asymptotically late. Yeah, because asymptotically we know it's -4. We are not interested in that we know. Then the early time tail would be kind of covered by quasi-normal modes, so you don't see it. It's with late tails, we need more this intermediate time tails, which have not yet this asymptotic behavior. And this was analyzed further by Marina in last year, where they published this paper, and they found that this picture of a single price tail, so a tail that really has a power law right from where you see it to the end, must be replaced by a superposition of actually many tails of higher power law exponent. And only if you really take into account this many components, you get an accurate description of the intermediate or late time tail. Yeah, so here they do this for eccentricity 0.9. And you see, if you only take a power law exponent, a single power law, your curve would be here. And they have to go up to 500 power laws that are stacked on top of each other to actually get an accurate description of what they see in the Raggeville-Cirilli solution. Okay.
Sorry?
Yeah, question.
If I can interrupt,
Sure, of course.
what is if there is any physical intuition of why you need to stack so many tails at the same time? Because I mean, I can always take as many parameters as I want to fit something, and then I'm happy about it. But
so maybe this is just related to their ansatz. So they make this ansatz of taking, of describing this by just a superposition of power laws. And if you make this ansatz, you need 500. If you make a different ansatz for your tail, of course, maybe you could have less functions, but then what function would you use? Yeah, so it seems to them at least, it seemed most logical to have a superposition of power law terms. So you could maybe think, so the power law behavior depends on the mode, right? On the L and M numbers. No, actually, I think mostly on the L number, right? The angular momentum, no, yeah, the angular momentum number. And maybe the picture is that the high L modes, they decay faster. But at this time, you still have to take into account a lot of these L modes that are still there and still affect the dynamics of the lower L modes as well. Yeah.
So these 500 exponents are fixed by, the exponent is fixed by theory. No?
Yes, they are fixed by theory.
So are they fitting the amplitude or?
They are, I think not.
So the amplitude is also given?
Well, so the whole system is scale invariant, right? So the only thing that matters is so the ratio between the small particle mass and the black hole mass. But you can increase the mass of the black hole, and that changes the whole amplitude. But once you do this ratio, I think it's the amplitude is also fixed. As far as I understand. I mean, I'm not an expert for exactly their calculations, but the amplitude should also be fixed. Yeah. More questions?
But if I understood correctly, like this sum is justified by, sorry, or summing or all else, or yeah, like okay, you truncate, but what I mean is like, couldn't you sort of just take one L and see that it fits each individual decay exponent or something like that?
Yeah. So asymptotically, so I mean, this is a one for the 2-2 mode, right? So this is for a particular L. And asymptotically, this would be, this has a defined power law with -4 power law exponent. But here you need 500 power laws stacked on top of each other.
Okay.
Yeah, maybe, so I don't know why, but my interpretation of was that the impact of the higher modes, I mean, the modes, they are all coupled, right? Maybe they impact also the 2-2 mode, but as they decay faster, eventually they don't matter anymore.
Okay.
Okay, so that was the overview over the perturbative results. Now I come to the nonlinear numerical relativity simulations. And with these tails, there's one big problem. They are really small. And because of that, any inaccuracy in the boundary conditions might actually modify the tails so much that they are completely off. Yeah. And so this has been demonstrated, for example, in 2004 by these people here. And they have studied this problem in spherical symmetry. This is scalar field. Yeah, so they have some scalar field pulse coupled to the Einstein equations, and then the pulse goes out. And okay, you see in the scalar field also some quasi-normal ringing, then a tail. And then when they put the boundary at 200, yeah, then the pulse from the center goes to 200, is reflected at 200 and comes back. So, and then at time 400, you see the reflected pulse comes here and destroys this tail completely. Yeah, there's no tail structure here anymore. But when they take the boundary at 500, then the reflected pulse would only come back at 1000. And then they see, okay, this tail is actually preserved, but you have to push the boundary further out. You just have to avoid that the boundary conditions can ever reach the point at which you look at the wave. So that's of course a problem. And yeah, a few months later, there was also this paper by Dafermos and Rodniansky where they made a formal mathematical proof that in this system of the scalar field, capital GR, any Sommerfeld and in more general radiation conditions lead to decay faster than any polynomial order. Yeah, so if it decays faster than polynomial, there's no chance of a power law tail. So we sort of have to work around this. Yeah, so, and I mean, this figure already shows us what we can do. We can just push the boundary further and further out until eventually our numerical domain is not in causal contact with the bad boundary conditions that we have. Yeah, so that's a simple, straightforward method if you don't know what better to do, sort of the brute force. But of course, it's costly. Yeah. So there are better ways. Yeah, you can think maybe there are ways to improve the boundary conditions. So that's an endeavor basically done by Rüter Buchmann and friends. You can try hyperboloidal foliations. I think there are some people here who work on that. You can also try Cauchy characteristic matching. Actually, there was also the same month, kind of coordinated with our paper, a first working Cauchy characteristic matching approach to this. So, but yeah, I am a simple man. I go with this simple method of just pushing the boundary far, far out. And because SpEC is so efficient, we can kind of afford that. And this SpEC code, I only give a brief introduction to SpEC. When I say SpEC, it is pseudospectral numerical relativity code. It stands for spectral Einstein code. It's developed by the SXS collaboration. And if you want to know more about the collaboration, you go to black-holes.org. There you find what you will need. So the physical setup is really easy. So we take equal mass black holes. Yeah, for the paper, we have also done unequal mass, but the curve is really just the same once you rescale appropriately. We take non-spinning black holes, and it's just a head-on collision. And then if you would run a usual SpEC simulation, your waveform would look like this. So you have here some initial transient with high frequency noise. So that's sort of the junk radiation. Yeah, then you have here the merger, quasi-normal ring down, and usually, okay, here maybe you think there might be a tail, but usually your simulation stops here. Yeah, right, 100 M after merger. That's what we know. Usually at that point, the simulation just is into the noise. So that's that. So we had to do really dedicated simulations where we just make the simulation really, really long so that we can see the tail. And that's what I show you here. So that's now a really long tail, 500 M from the merger. And you see, okay, you have the 2-0 mode. which is clearly visible, has also very clean tail. And then you have here something here, maybe that, I mean, that tail doesn't really look correct. So these tails at higher L, they're maybe not very well resolved. But okay, we can see the tail here. That's really nice. So, however, here the boundary is actually very close. Is in causal contact with where we extract gravitational waves. Yeah, in fact, if we were to compute at what point is this waveform in causal contact, well, it would be at minus 1100. So everything we see here has causal contact with the outer boundary. So why do we see a tail here? But back in 2004, they showed that in a scalar field, it's not possible. Yeah, so initially we weren't really sure whether this theorem that Dafermos and Rodniansky prove will apply to this case, because they proved it for the scalar field. But here we look at, yeah, I mean, here we look at the news. So, but you can think also of psi4 and the gravitational wave degrees of freedom. They have a little bit different decay behavior than a scalar field. Yeah, so a scalar field decays like 1 over r. And also the reflected pulse has this 1 over r behavior. But in NR, sort of the incoming radiation is psi0, which has a different fall off from psi4. So maybe this whole theorem actually does not apply exactly. And maybe this saves us here. We didn't do the formal proof, but what we can do is we can just make a numerical test. Yeah, we can take, so here, this is a schematic diagram of where our outer boundary is. So this is our outer boundary here. This is our extraction sphere. So actually we have several extraction spheres that are here in this region. And this is a black hole. So you have one black hole here, the other one would be here, sort of. Yeah, they merge, and then the black hole rings, the stationary black hole rings, the black hole rings down, going to a stationary state at the origin. Yeah, and now we can make the outer boundary so far apart that basically what comes, the signal from the merger, once it's extracted here, nothing has been in causal contact with the outer boundary. Yeah, and we want about 500 M. So if this is 500 M, even here, nothing will be in causal contact. Yeah, and if it's in causal contact, we just put the outer boundary further out. So what do we get? So we get these 4 curves, which should all be identical. But we have this one, which I showed you before, which has that one should be blue. Okay. So this one should be the blue one. So this has causal contact at minus 1100. This one has causal contact at minus 100, about here. And you see, okay, they are completely different. Yeah, that means somehow the boundary conditions for sure make a difference. Yeah, this tail is not at all believable. Yeah, so the ring down is perfect, in perfect agreement, but this tail is completely off. Then we have the green one, which only gets in causal contact here. And that's this curve. And then we have another one at 8,000. Okay, causal contact is here. And it agrees with the green one. Yeah, so that means, okay, that confirms that we really have to be very careful about not being in causal contact with the outer boundary. Yeah, so even if it looks like a clean tail, it's not. It's just rubbish. So then, okay, we said we do these expensive simulations where we push the boundary further out, and then everything works. We did a few more convergence tests, like we want the black holes kind of to approach from infinity. So we also, but in our simulations, they start at 100, 200, or 400 M. So we kind of have to make sure that we don't have too much of an error due to starting at a finite distance. No, they don't start from rest. We set up the initial data such that the ADM mass is 1. Yeah, so that means if they were to start at infinity, they would be at rest at infinity, but at 100 they are no longer at rest. So, and okay, the curves are really close together. We also made this test with resolution. So left 3 means very high resolution, left 2 intermediate, left 1 is our lowest resolution level. We also make a test with the extrapolation order, yeah, because we have to extrapolate them, the waveforms, to infinity, or future null infinity. And we also compare to the perturbative simulation again, which you have already seen. And okay, this is in percent. So we see the difference in resolution is about, so for the tail is about here, so that's about few percent. So quite good resolution or quite good result for the tail. So we are definitely not too much affected by finite resolution. And also the extrapolation order only changes by, I don't know, maybe it's also less than 10%.
Then could it be that the difference between the perturbative and the numerical is because of the resolution? Or no?
Well, no, at least not in the numerical relativity simulation resolution, because you see the difference to the perturbative one is larger than the difference between resolution. Yeah, so this is 1% error, this is 10% error. So it cannot be explained by resolution. Oh, Cauchy. Cauchy characteristic extraction and matching. So for the simulations that we have done, we can extrapolate the waveforms to a future null infinity. But nowadays, there's also a lot of technology to actually do the Cauchy characteristic extraction, which should in principle be better than an extrapolation, because for the extrapolation, you have to make assumptions and so on. But for CCE, you also have to make some assumptions for the initial data of your CCE. So, and you see, when you take our simulations and you do a CCE extraction, then the results depend quite strongly on the initial separation. Yeah, it depends on the initial separation. Yeah, which wasn't the case for the extrapolation. So something is not yet quite understood for CCE, maybe. Yeah, the initial data is maybe not perfect. But at 400, it matches quite well.
But will the CCE take as even data like data on the boundary. So, even if it's not in contact with the constant contact, maybe you took something from the boundary that is weird or something. I don't know, like with words.
Well, you wouldn't pick up anything from the boundary. Yeah, so because, so if I reproduce this diagram here, so this is where so this is our outer boundary. Yeah, so this is the outer boundary. This is where we extract. And really our wave extraction, the CCE wave extraction will start from here and use only data here. And maybe from the past data that you assume on a future null infinity. Yeah, so if you remember what Edgar was telling us yesterday, yeah, you need data at future null infinity and basically this null rate, right? But you don't need any data in between. Yeah, so whatever is at this boundary does not enter here.
Okay.
So
As long as you keep that boundary, the numerical relativity boundary, causally disconnected from the extraction.
yeah, of course. So if kind of if your speed of light was such that this reached here, of course, then everything here is affected by the outer boundary, and then it would be affected, but it's not. Yeah, it would only reach here, and at that point, you have already extracted it from there. So, and then in December, there was also this paper by Zheng, who implemented the Cauchy characteristic matching approach into spectra. And he has done, yeah, also a head-on collision. And he has basically done a similar approach. So he has done a reference run where he put the boundary really, really far out. Yeah, and then he gets this nice tail. He has done a run where the boundary was not far out and has used CCE to extract the waveform. And he has done a simulation where the boundary was not far out, but at the boundary he used Cauchy characteristic matching to impose the boundary conditions. And then you see you also get very agreement with the tail. Yeah, so that's a really strong indication that his Cauchy characteristic matching approach is actually quite solid and solves a lot of the problems that we have with boundary conditions in numerical relativity. And okay, he is also doing a fit to the tail, and he gets minus 1.79 for his power law exponent. Yeah, and I bring you up this again. Yeah, as I've told you in the beginning, this power law exponent isn't immediately asymptotically at -4. Yeah, so this would go to -4. And here's also kind of fitting this region, which for us goes from -1.5 to -1.8, 1.9, I don't know. And he's fitting this region, so he's somewhere in here. So also our results agree quite well. So this is sort of, okay, this plot is also sort of the summary of this talk. So any questions so far? Yeah, Nicola.
What is the oscillating behavior between the different mass ratios?
I don't know. So the power law exponent is a little bit difficult to extract because the data is a little bit noisy.
So but this is the numerical data or is the extracted?
So this, what do you mean by extracted?
I mean, is it like the fit or the numerical data?
So you take this line and then you assume that this line satisfies a power law. And then you can take the derivative of it, I think. And once you have, when you have this power law, you take the derivative, then you divide by the field, and you get the local power law exponent. So, and taking this derivative is a numerical procedure which introduces some noise. Or yeah, it enhances maybe any. Yeah, so you kind of see maybe inaccuracies enhanced in this power law exponent. Yeah, because even if you see the power law sort of oscillates like that, here actually it's you don't see it. But also, maybe I go back to the very beginning. Yeah, so when you remember this slide, see also in this Reggie code, you have these many tail components, and they can interfere. Maybe the interference between these tail components causes oscillations. Yeah, so these oscillations are actually real. It's just that the different components interfere with each other. And maybe it's the same that we see in that plot. It's a little bit of a guess, yeah.
And what about the starting time for the tail?
So for the perturbative approach.
I'm just for the fit.
You mean here for what Xi Zheng did? Yeah.
Yeah, also like when you try to extract its connection to the exponent. Like what do you decide when the tail is starting?
So I mean this one is a local power index, right? So you take this region, take a numerical derivative around this region. So there's no fit in this plot, but here they were doing a fit. And well, I don't remember where they started, but it went a little bit into the ring down regime that I know. So, okay. So I told you already in the beginning that we don't really know what is the cause of this small disparity between NR and the perturbative calculation. Yeah, maybe one has to go to a second order perturbation theory, or maybe one has to take into account higher order cell force contributions. That's for the perturbative people. Yeah. And so we have also seen that these tails are really sensitive to this long range structure of the space-time. Yeah, the boundaries that are far out, they are important. So one might ask the question, is it possible to probe with the tails sort of the environment of the black holes? Yeah, whereas quasi-normal modes, they mostly depend on the physics of the black hole locally, but the tail would maybe tell you something about the environment. Yeah, but of course the tail is super small. So, and it doesn't oscillate. So that means in your wave detector, maybe it's outside of the frequency range of your detector. It's super small. So there's a question, would these tails ever be detectable? We don't know yet. Maybe if there is an impact from the environment, maybe the environment introduces oscillations in the tails that then tell us something. So that's it. Thank you. Any more questions? Yeah.
Like, for example, so imagine you're in a hyperbola forest.
Mhm.
Of course.
So, I mean, yeah, like, how careful would you need to be with the boundary conditions, for example, at square? You know, like, for example, yeah, what would be the threshold, let's say, for, you know, how precise should they be, you know?
Uh-huh.
I don't know if you have a question to that.
Well,
I mean,
So, I mean, in principle, there shouldn't be anything coming from square plus, right?
yeah, that's
So you should be, probably you should be careful to not send anything from square plus.
Yeah.
Yeah.
okay, yeah.
But in that case, where exactly are you extracting the state?
On a hyperboloid slice, you would extract it at square plus, yeah.
Well, I think that, well, we can focus on-
I wonder if so you were showing the discrepancy between the perturbative calculation and the numerical one. I wonder if, say, nonlinear effects in the perturbative case are also enhanced by eccentricity. So if you were to do, instead of head-on, you know, like less eccentric orbits, you would expect them to match better, like the higher order. I mean, at least to sort of think if that is the case or not, right? Are you planning to do that? Like, or can you, like, say, until which eccentricity can you use to capture the tails in the numerical relativity?
Yeah, well, that's a good point. So, yeah, I mean, one thing is I think the most difficult problem is that once you have an eccentric orbit, maybe it does several orbits, your simulation becomes much longer. Yeah, so here we were able to push the boundary far out because the simulation wasn't that long. Yeah, but if you have to wait for several orbits, well, your boundary has to go several orbits in time out, right? So the cost sort of doesn't scale very well with the number of orbits, at least in this approach. Yeah. So, but hyperboloidal or Cauchy characteristic matching, there it would probably work. Yeah. Which hasn't been demonstrated yet, right? So Xi Zheng only showed also a head-on, but I think that's the next thing they will do. Yeah.
I'm interested about CCM actually. I know that's not what you did, but in these head-on collisions, which would be kind of the best case scenario for just putting the boundary farther away, do you have an idea of what is the kind of cost comparison from doing CCM or putting the boundaries far away?
So, well, CCM requires you to do the Cauchy characteristic evolution, which so it's how many variables? 4. So I think you sort of evolve ODEs for 4 equations at over 100 or 200 points. So I think CCM adds only little overhead.
Oh,
yeah.
In this case, it would be much cheaper than the bigger.
Yeah, I think it would be much cheaper. Yeah.
You were saying that normally the simulation wouldn't run for so long. So what did you need to do to make it run longer?
Basically, just change a parameter in the code. Yeah, so we had a hard-coded value of 100 M after merger, and you change that. And well, you have to also think about we had to put your extraction spheres and so on, but yeah. Joao.
Regarding that difference between the perturbative calculation and the numerics, do you have any idea how this disparity evolves during the evolution time? Because it seems that it only becomes visible at the end of the plot. But since you're plotting in log scale, this could be just something that's like there from the very beginning, from the the parts of the merger where nonlinearity should be most important, and then just ignore it and not see it at the end. That's what's happening. Or if it's actually something that builds up during the tail excitation. Not excitation, but during the part that goes over.
Let's see if we can we tell this from here? This is a residual, but okay, it's a relative residual. So it seems to be almost always 10%, right? That's, I mean, okay, also here in the cardinal modes, it's oscillating sort of at the 10%.
So it could even be something that's happening way before you start seeing tails, that you're only seeing there because you've reached this very small value.
Yes, yes. I mean, actually, most of these tails, they come from the past, right? Yeah, that's why the eccentricity matters. Yeah, so basically these tails, everything comes already from the past when we don't see them. But yeah, I mean, here the value changes. Okay, the value changes by factor 10, maybe. But the relative error is about 10% all the way. So I would say,
Yeah, but the percentage was more or less the same.
yeah, but this indicates that actually it's not a constant.
Yeah, it's
But the absolute magnitude or the absolute disparity is actually decaying, but the relative is increasing. Yeah. Edgar.
So, one question, so here the linear evolution is not, I guess, with the standard method, not with the hyperboloidal or Rodrigo, right?
So I don't know. Okay, I don't know what Rodrigo did, but so they are using. Yeah, they have a. It's an.
They use hyperboloidal.
Yeah, yeah.
Not holidays, but I have a follow also there.
Because my question was if like you do the linear thing, I mean, my question is like the discrepancy between the linear and the non-linear, how much is it because of the boundary? Because you are not really completely fixing it, and how much of it is because of the non-linear, the fact that it's non-linear, right? Like if you compute polynomial modes and the tails and everything, using, for example, Rodrigo Panos and Macedo's hyperboloidal approach,
Yeah.
do you get a better thing that approach is more closely is closer to the nonlinear thing, or this is just to be the nonlinear effect? So my question is, what is more important, the nonlinearities or the fact that you can actually put or not boundary anything?
So yeah, as Jen said, they are using a hyperboloidal layer. But so, but you say for even if you use a hyperboloidal layer,
No, yeah, my question is, I mean, so hyperboloidal layer, I mean, they use a hyperboloid for the linear thing.
yeah.
Okay.
Yeah. So it's this code. It's called RWZ by yeah, who was it? Sebastiano Bernuzzi and Alessandra Nagar. They love this. So and the Hüb is for hyperboloidal, right? They have a hyperboloidal layer.
Okay, so the linear part is already with the optimal version that you really copy things like right.
Yeah.
You mentioned about
possible to be the environment. Time the plan doing exploration, some matter content, to localize some kind. Represents some sort of environment.
So I don't plan that at the moment, no. So what meta model would you like to see? So probably a scalar field.
Oh, I don't know, something that can be more localized. With more like
Hey, you want to see an equation disk? Okay.
Because you're saying that the boundary condition can't kill the tail, so if you have some magnetism, then that scatter the waves back.
Probably it would perturb them in some way, yeah.
Well, I want to know, so you mentioned that these tables like can build up in evolution, like are there from the beginning. So why didn't I didn't understand why didn't you see that much difference when you changed the initial separation? Because in some sense we shouldn't think that these tails are already present in the initial tail.
Exactly. So I think the reason is just, so you are talking about this plot, that 100M is already big enough to kind of build the tails during the inspiral, well, not an inspiral, but during approach of the black holes, yeah.
So if you were to try putting them closer and closer, you would expect to see less and less.
Yeah.
I think that the point of stable excitation is that you have to have, like, they have to be close enough, no, they have to be far apart, right? That's relatively close to merger, because if you put a very, very large distance, yes, you're starting to excite tails earlier on, but they start to decay earlier on, so that's not quite related to speed. So somewhere in between.
If you enjoyed the video, like and subscribe.